Okay. So continuing with the examples, this is example 5 dash, or problem 5-136E in the text. All right, so we've got a container. It's a rigid container. What does that tell you about the volume?
Doesn't change.
Doesn't change. It's 60 cubic feet, no matter what. Initial pressure, 75 psia. This is just air, by the way, so we know the properties to look up. And a temperature of 120 degrees Fahrenheit. Electrical work comes in, and there is no heat transfer. Okay. Now, the valve at the top is opened and some air escapes. So the pressure is 30 psia, and the temperature is 120 degrees Fahrenheit. Okay, now let's think about what happens in terms of energy first. That's the way you should always start these problems. Did we start off with more energy in the system or end up with more energy in the system? What do you think? Let me give you a hint. This is a tricky hint. The temperature is exactly the same, and the energy of an ideal gas like air depends only on its temperature. Now, do we start out with more energy or end up with more energy? Or are they the same?
It's an ideal gas.
It's an ideal gas. Because it's air. Trying to push it to a hole here. Thanks for following the The amount of energy per mass stayed the same, but we have less mass over here to hold it than we have over here. Does that make sense? It's like each person in here has $50 and each person in here has $50. That's what this temperature tells you. There's more people over here.
So the specific energy stayed the same.
Specific energy stayed the same, but total energy changed. Okay? Now, could you figure out how much mass there is in state 1 and in state 2? Sure. We have the volume in both. We have the temperature and pressure in both. So coming up with a mass will be pretty straightforward. In fact, I won't bore you with the details. I'll just write down my results. The mass, P1, V1 over R over T1, assuming we change this, of course, to Rankine, is about 20.95 pounds mass for state 1. And for state 2, doing the same thing, P2, V2, pardon me.
Bless you.
Thank you. V2 over R over T2, and we get about 8.38 pounds mass. Now, I mentioned energy. Could we go ahead and figure out how much energy is in each of these tanks? Sure. Because we could basically determine that the amount of energy per unit mass is the same in both. So if we could just figure out what that is, we would do it. Well, it turns out that there is a handy table in your book that is an air table. Look at table A17E in the back of your book. Sometimes we use CB delta T. Sometimes we use CP delta T. Sometimes we'll say, forget it, let's just go look it up. We can do that as well. 220, we didn't have a table of air properties. In this class, in this book, we do. There's a reason for that. It's because that you don't really need the table, but it's handy to have. Now you can be spoiled a little bit since the problems are harder. Okay. This is a table that is worth bookmarking. It's properties of air. You can look up the internal energy and the enthalpy of air as a function of temperature. Which one should I look up? If I want to know how much energy is in the system in state 1, I'd like to know the total energy. I'm going to multiply the mass in state 1 times the specific internal energy. I just gave it away. I'm trying to ask you which one do we want to look up, enthalpy or internal energy. So why is it internal energy? Flow energy, that's right. So coming up with the total energy in states 1 and 2 is pretty straightforward. All we have to do is use this temperature to look up U1 and use the same temperature to look up U2, which by the way is going to be equal to U1. Okay. So what is the specific internal energy?
98.9.
That's BTUs per pound mass, and that's at 120 degrees Fahrenheit, right?
581.
Okay, so you went ahead and added 462. Okay, thank you. So there's the amount of energy per unit mass. So we can multiply 20.95 pound mass by 98.9 BTUs per pound mass. And if you do that, let's see, I didn't do that. If you guys wouldn't mind, go ahead and carry out that multiplication. Sounds like a good year to me.
Sure.
How about over here for you two? That would be 8.38 pound mass.
We got 2071.
For this, 2071 or
2072, actually.
Oh, we went from the past to the future. 2072. All right, so how about over here? Well, we need to multiply by 98.9.
I'll just do it. My bad.
No problem. BTUs per pound mass.
828.
How much?
828.
828.8? Thank you. And that's just BTUs. So what we've just done here is we figured out the bank account balance, right? This is what the system started out with, 2,072 BTUs. It ended up with about 829 BTUs. Where'd all that energy go? It's carried out. Now be careful here. There was actually some energy carried in here as well. It's interesting that despite the fact that some electrical energy came in, overall energy in the system was lost. A lot more was lost, that's right. In fact, the air that escaped, what forms of energy would it have carried? Flow and. Okay, so it carried enthalpy, that's right. So we have a kind of a nice problem here because the temperature didn't go down. If the temperature had gone down, what we would do to estimate this is very important because this happens in some problems. What we would do to estimate the enthalpy here is we take the average temperature and that's the temperature where we'd evaluate the enthalpy. In this case, since the temperature is the same, all we have to do is look up the enthalpy at 120 degrees Fahrenheit. So you guys read off for me U just a minute ago. Same line, read off H, please.
138.66.
So that's how much enthalpy the leaving air carried with it. Now, how many pounds of air escaped? The difference between 20.95 and 8.38. Basically, what I just said was an energy balance, or was a mass balance, right? All we have to do is take the mass in state 1 less the mass in state 2 equals the mass that leaves or goes out. So the mass in state 1, 20.95, less the mass in state 2, let's make it 829. What am I doing here? I'm trying to go for enthalpy or energy, aren't I? Okay, mass, here we go, 8.38, let's try that. And that's pound mass. Okay, so take that difference, it's going to be a little more than 10.
It's 12.57.
12.57? Thank you. So there's the mass that leaves. Okay? Could we quantify how much energy that mass carried with it? Sure. Take the product of these two, right? So the total enthalpy that leaves would be equal to the mass that leaves times the specific enthalpy, or the amount of enthalpy per mass. Okay, so the mass that leaves, we just figured out, was 12.57 pound mass. The enthalpy is 138.66. Sorry, I'm running out of space here. Let's move this. 138.66 BTUs per pound mass. Same trick we pulled with the air inside of the tank. So multiply those out if you would please and tell me how much energy leaves. 1743 BTUs. Wait a second. What's the difference between these two? Sure not 1743, is it? Okay. So what we need to do is apply an energy balance and answer the question of where did the extra energy come from? Because it sure didn't come from all of this, right? Some of it had to be supplied by the electrical work. In fact, one of the questions is, what is the electrical work again? Well, let's just write down our energy balance and find out. All right. I want you to help me here because this is a pretty simple problem. Are there any deposits? If so, tell me what they are and tell me whether I should make them positive or negative.
Electrical work is in deposit.
The deposit, is it positive or negative?
Positive.
Positive, because it adds to the system. Any other deposits?
So boundary work?
Is there any boundary work?
No,
No.
volume doesn't change.
Volume doesn't change, so it can't be the boundary work. If you're thinking that this air pushes the atmosphere out of the way, you're right, but that's accounted for in the end. That's accounted for the flow energy of the Okay, so what else is there? There's no more deposits. Are there any withdrawals?
Withdrawals, yes.
Pressure drop.
Pressure drop doesn't mean a
Well, but
withdrawal.
the enthalpy withdrawal.
Enthalpy change.
You mean the mass that comes out that carries out, right? So minus the enthalpy that leaves. Enthalpy that goes out, that's what that zero or O stands for. This is a deposit, this is a withdrawal. How about the account balance? How about what's inside of the system?
We already have those, but
Did we? We've calculated their magnitude, but have we put them in the energy balance? Haven't accounted for them yet. So basically what we need is the final minus initial. Right? It's always final minus initial.
U2 minus N1.
So in other words, capital U2 less capital U1, since we've got those as numbers. Okay. All right, so the electrical work that comes in must be equal to U2 less U1 plus HL. I think it seems like I made a mistake here. Let me think for just a second. Supplies that and supplies. Yeah, we've got a negative.
It'll be positive.
Oh, each other's electric. Well, for some, I feel like these two should be flipped. But,
no, it'll make
It'll come out positive.
Your HO will make it.
yeah, I know it will, but what I'm saying is, to me, it looked like the system gave up some of its energy that
Make
this
it
did not
actually
have to
value.
provide. Oh, that's why it's negative. Okay, yeah, I'm okay now.
Why is it negative?
Because basically this is subtracting from the energy that this had to provide. So U2, no, what is it? That still doesn't make sense.
Because you said you have to make a final minus initial.
Right. And
So
it
that's
should be-
just it's the energy lost at that state.
Well, it should work out. Let's plug it in and see what happens.
I say if you plug it in that way, you get about, it's 499.8, so basically 500 BTUs.
That's right. Yeah, that's right. 2072 plus H naught, 1743. These are all BTUs. And you say we get about 500?
Yes.
Let me think for a minute. No, yeah, of course. No matter what we do, the air is going to leave and take that much energy with it. This subtracts from the energy that the work has to provide. So that doesn't make sense. Well, this was a pretty easy, unsteady problem. It was straightforward. Because all the pieces fell together pretty easily. Let's work another problem that's not quite so easy. This is problem number 142. an adiabatic piston-cylinder device equipped with a spring. This is, by the way, the figures on the top of the column, on the next column. Maintains the pressure inside of 300 kilopascals, or at 300 kilopascals when the volume is 0, and 3,000 kilopascals when the volume is 5 cubic meters. The device is connected to a steam line maintained at 1,500 kilopascals and 200 degrees Celsius, and initially the volume is 0. Determine the final temperature and quality, if appropriate, when the valve is open and steam in the line is allowed to enter the cylinder until the pressure inside matches that in the line. Also determine the total work produced during this adiabatic filling process.
Wow.
That's a good question. What is adiabatic?
No transfer across boundaries.
No heat transfer across boundaries. All right, so let me write down the problem number and make a couple of diagrams here to show what's going on. So this is problem 5-142. All right, so we've got a spring connected to ground that comes down to a piston in the cylinder. The initial volume is 0. Now, I know I've drawn it with some volume, but that's just so I have some room to write things in. Okay, we've got a supply line with a valve, so we can turn it on and off. Supply line supplies, what is it, steam?
Yeah.
So steam at a pressure of 1,500 kilopascals and a temperature of 200 degrees Celsius. So we're going to open the valve and let some mass come in. Now, Mr. Beck was right. Adiabatic means that there's no heat transfer, Q equals 0. Now, one of the things that they told us is that the spring maintains the pressure as a function of volume. They gave us that. It basically said that if you look at pressure versus volume, we'll just use total volume because that's what they use, kilopascals versus cubic meters. At a volume of 0 cubic meters, the pressure is 300 kilopascals. But at a volume of 5 cubic meters, the pressure jumps up to 3,000 kilopascals. What do you think the pressure looks like in between those 2 points? Linear. You're right. How do you know that? It's a linear spring. Now, there's no such thing as a real linear spring, but most of them are close enough to be approximated that way. So we're going to take this system and go from no mass in the system to the point where the pressure in state 2 is 1,500 kilopascals. Now, wait a second. They said that the pressure goes up to 1,500 kilopascals, I'm sorry, to 3,000 kilopascals, when the volume is at 5 cubic meters. So could this be 5 cubic meters? No. Basically, they gave us this graph, and what we have to do is figure out that we only go up to 1,500 kilopascals. So what volume do you think we ought to read off? So it's almost like a linear turbulation factor. That's basically what it is, right? So all I'll do is I will take this side as a percentage and this side as a percentage and calculate it. So we'll do that in just a second. But basically the spring is all compressed now and the piston has moved up. And we've closed off the valve so that the mass in the system is okay, so let's see. Let's figure out how much volume the system has in state 2, because this would be the volume in state 2. Notice this is the volume in state 1. So we know the pressure in state 1 is 300 kilopascals, even though the volume in state 1 is 0 cubic meters. We know the pressure in state 2 is 1,500 kilopascals, so how will we figure it out? Well, we'll stop playing with it and we'll do it. V2 less 0, which is this distance, divided by this distance, 5 less 0, would be equal to let's see, I took this distance over this, so I better take this distance over this. So 1,500 less 300 over 3,000 less 300. Okay? So all I need to do to get V2 is multiply 5 by this ratio. So this is 5 multiplied by, let's see, 1,200 divided by 2,700. So the volume in state 2 is 2.22, and you can see my scale's off a little bit then. So V2 is 2.22. Now we know along the way we'll have to do an energy balance, and we can already see that there's some boundary work associated with this process. Why don't we just go ahead and calculate how much boundary work there is? How would we do that? Well, we just have to remember that boundary work is the area under the curve. Boundary work is the integral of pressure over volume. Here's a volume change. Pressure changes as a function of volume. So if we get this area, we can get the area under the curve, we can get the boundary. Okay? Well, that's not too bad. Turns out there's an equation in your book that will help us with this. Let's see. I don't remember if you guys pointed it out. No, that was really last time. Let's see. I think it's at the back of the chapter in summary, if I remember right. Nope, it's not there. Maybe in this class it's in a example problem. It's pretty easy to see. So I won't bore you with it. Basically what you do is you use an average pressure, which is just P1 plus P2 over 2. And you use the difference in volume, V2 less V1, that's the distance here, you multiply it by the average pressure height, and you get rid of that shape. Okay? I'm sorry? Yeah. Basically. So the boundary work then comes out to 1/2 P1 plus P2, so we're just taking the average of P1 and P2, multiplied by V2 less V1, but V1 is a 0. So anyway, when you plug in all the numbers, you find that the boundary work is about 2,000 kilojoules. That's how much boundary work left this system. So speaking of which, we probably ought to start keeping track of energy flows. Okay. So boundary work left, we figured out the magnitude of it. What deposits did we have? We really had one, right? We had a deposit right here, steam flowed in. And that mass carried energy with it. We had one withdrawal right here, and then there was a change in the energy of the system. So let's write down the energy balance and see what we're looking at. We have to find and plug into it and solve this problem. So the energy balance, let's say the energy that flows in less the energy that flows out is equal to the change in the energy of the system. It's like we used before. Expanding these terms, you guys have already decided, along with me, that the mass that flows in times the enthalpy that it carries is the energy that comes in less the boundary work which leaves. Those are the only deposits and withdrawals. This would be the internal energy in state 2 less the internal energy in state 1. That's the bank account balance change. Now U1 is 0. How do I know? No mass. It may have pressure, but there's no mass. Now how could it have pressure? Well, if the spring had the piston set on the bottom of the cylinder here, it's pushing, there could be pressure. It would be force per area. But there's no gas in there to experience that pressure. So that one's gone. So what do we have? Well, we've got this piece. Could we give the enthalpy that comes in? Sure, we can look it up, right? Because we've got the pressure and temperature of the incoming gas. So try to look it up and see what you find.
Is it just steam?
It's just steam. I believe it's steam.
It's What's the pressure?
1,500 kilopascals. It should be superheated.
No.
Did we run out of table?
It's in between.
It's in between?
Oh, darn.
Well, no wonder I cheated. I used ease to look it up. The enthalpy end comes out to 2796 kilojoules per kilogram. I probably rounded it off.
So on the pressure table, and I don't know the temperature corresponding here, we've got 2791.
It's pretty close.
What's the temperature you got?
200.
This is 198, so yeah.
It's close. Yeah, it's really close. Make that proper too. So we got the enthalpy that comes in, that's not a problem. Let's get rid of U1 since it doesn't exist. How about U2? Why don't we write it this way? How about M2 U2? And notice from the mass balance, the mass that comes in is equal to the mass in state 2 less the mass in state 1, but the mass in state 1 is 0. So these two are the same thing. So these are just one unknown.
Would the temperature be different and therefore messing with our mass? Since it's a lot to flow in?
We don't know how much mass comes in yet. All we're doing is showing that mathematically, however much mass comes in is the mass that's in the system in state 2. So we don't know what it is yet. Does that make sense?
Yeah, I'm thinking computing an aspect.
All right, so what do we have here? Well, let's see. Holding this down, let's get rid of, what did they ask us to find? I didn't even bother considering what they asked us to find. I think they wanted us to find the temperature at state 2. That was the main goal. Let's see, 142. Yeah, determine the final temperature and quality if appropriate. Okay. Well, let's see. Since it really doesn't matter which one we eliminate, I'll just eliminate MN. And so M2HN less boundary work is equal to M2U2. Notice we don't know M2 and we don't know U2. These are two unknowns in one equation. We use up the mass balance, we don't have that to deal with. So what could we do? There's a constraint here that's not really obvious. Notice that we know the volume in state 2. If we know the volume in state 2, then the specific volume in state 2 would have to be equal to the total volume in state 2 divided by the mass in state 2, right? Notice the mass in state 2 is one of our unknowns. But we know this. And if we knew U2, we could read off V2. These two are not independent of each other, right? Because the pressure is already set. And once you set one of them, the other one will be set. Because all we need is two properties in order to fix the state of a simple compressible system. So these two are not independent. In other words, if we could find the exact right spot on the table, we could read both of them off, plug them in, and they would solve this equation. It would work just fine. Okay? Unfortunately, that's a lot of work. So it's nice to have ease that has property data tables built into it. Because what you can do is give it all of these equations and tell it to go solve it. And then do it. And what we do is we go through the tables and find all the match, basically, where V2 and U2 are associated with P2 with the appropriate mass from these equations. So anyway, solving this with ease, the temperature in state 2 comes out to 233.2 degrees Celsius. Now you tell me, is that saturated or not? The easy way to find out is to look up 1,500 kilopascals in your saturated steam table. I think it goes up that high.
higher pressure, then you
Yeah, you look at the saturated.
saturated, that's higher. Ooh,
It's
that-
lower
can't
temperature.
really tell from intuition because a higher pressure gives you a higher boiling temperature.
Well, we have to go look it up.
What are we looking at, saturated?
It's at
It's
190,
saturated.
it's at 190 degrees Celsius.
At 1,500 kilopascals, and if you're 198, we're at 233, so it's superheated. So we don't have to bother determining quality. By the way, at that point, V2 comes out to 0.1458 cubic meters per kilogram, and M2 comes out as 15.25 kilograms. Let's find out if E's did it right. Let's find out if it's solved well, we're out of time. It's solved it properly, you can check it later. Plug all those in the equations and work it out.